Yeah, just on that last question on the memory speed behind the buffer, the OMI bus at the 25 gig speed is basically a 50 gigabytes per second read plus write. It has one memory channel behind it. So you can saturate a read, or you can saturate a write, or you have 50% if you're doing simultaneous read-writes. So technically, one channel of DDR5 going at 6400 would then give you the balanced as well as saturating both. But in the Power 10, they've also upped the speed to 32 gig, and there's a roadmap to 38 gig, and beyond. So everything's, they're trying to keep up with the speed of the DDR5. I think DDR5 is 4800, then going up to 64, et cetera. Okay. Okay, so now I'm going to present on, give you an introduction to I'm the technical lead for the OCP HPC SubProject. My name's Alan Cantle, and we're developing a high-performance computing module. We've got a concept right now. It's not a physical reality. And I'm going to give you an introduction to that. The presentation is in four separate short presentations. I'll be giving 3 of them, and Chris Chapman, a colleague, there's Chris, will be presenting on some thermal aspects in the last presentation. So I'll get going with this. So what I'd like to first start with is what we're trying to do in our work group is we're trying to reinvent an open HPC architectures, but we're looking at it from a domain-specific architecture computing world. So we've got many heterogeneous processors to build from these days, and it would be great if we could pick best in class of everybody's processors and really connect them together into an HPC system. So it's taking the spirit of modularity of OCP, and really we're trying to revolutionize some things here. So we're trying to break a lot of eggs. And I've just put this chart up because just over a year ago at the Open Power Summit, I concluded that this is a nice abstract model, a nice template, the way to think about a data-centric world, like the cloud, the edge, and the IoT, with all the processors, the memory's in the center and the processors are on the edge. I try to get the world to do this. We're so in the habit of putting processors in the middle and building everything around them. Let's put the memory and the data in the middle and build around that. So it's a bit of an abstract view, but from an HPC perspective, this is a data center diagram, but from an HPC perspective, it's really becoming increasingly data bound and less so compute bound in the HPC world. We've been traditionally very compute bound, and that's becoming an increasing problem. This chart is a bit of an eye chart, but it represents the supercomputer roadmap. And the 2 circled ones, the one on the left is the Summit machine that was the #1 of the top 500 back in 2018 to 2020. And the one on the right is a new Frontier machine that's just being turned on anytime soon. The key thing here is I'm saying that we're seeing they are both heterogeneous, and we're seeing a blurring of the storage and memory boundaries. The Summit machine introduced persistent memory near to the compute, as well as the file system. And the Frontier machine is accelerating the size of the persistent memory compared to the main memory footprint and even the file system footprint. So you can see that trying to get near persistent memory is becoming more and more important. So why is that? Well, take a closer look at the Summit machine. The Coral Summit machine, you can see on the left, that's the main compute nodes, and they have 2.4 petabytes of DDR4 and 0.4 petabytes of HBM, and they also have 7.4 petabytes of persistent memory. Now, in the Summit machine, that persistent memory was used for checkpoint restarts. So if the machine crashed, you could really get back up and running really quickly. And it was not used for anything else, to my knowledge. Then on the right, you have the file systems. You have this 250 petabyte file system with a 2.5 terabyte per second link into the supercomputer through a power-hungry top-of-rack network. If you do the math on this, when you need to load the memory for the first time, if you've got a job that consumes all of that memory, it will take you 18 minutes to load the memory just with from the file system just once. So if you have a high-performance computing job that runs in 18 minutes, 50% of your time is loading the machine. That's a little bit of a problem. But this doesn't really cause too much issues in HPC because HPC is typically more compute-bound. You know, jobs run for ages on the one set of memory. But as you go more and more data-centric, if, for example, you wanted to stream the entire 250 petabytes through the supercomputer and only touch it once on a more of a data-bound problem, it would take you 1.2 days on the Summit machine to just move the data to the machine. And so this is becoming an increasing problem. We've got, in our work group, we have Lawrence Livermore Labs, we've got NASA, and they are saying this is a major problem in their systems. And this is why you're seeing this persistent memory come forward. So we really need to bring the two closer together. And that's something that is and now we're doing it slowly, and in our work group, we're trying to do it openly and more radically. So how can we do that? So just as a little bit of an abstract view, so if you imagine you've got one of your high-performance processors at the bottom, we want to get pluggable, we want to be able to plug in. We want memory, storage, and persistent memory. We want it all to be really just be seen as memory, when we're sort of beginning to see that with the likes of CXL. But we want many, many terabytes to be close to this processor if we really want to work on data-bound problems successfully, whether it be volatile, persistent, or file system storage memory, and being pluggable. We really want a low-power interface from that memory to that processor. Around about a picojoule per bit would be a great start. Lowest latency possible, highest bandwidth, pluggable, near-memory interface is what we'd like to get to there for the best performance. And these different media, we really want to put distributed compute, because if you can actually compute in the memory or in the storage itself, with tiny little processors, and not move it to the big processors. So these storage media devices, memory devices, could have some compute in them, but relatively speaking, a tiny resource. And finally, you want to efficiently share the processor's near memory with other processors, so you'll have a high bandwidth memory pooling data plane. So this is the building block of the supercomputer that you want to start with if you're bringing data-centric. If you're addressing the data centricity problem, as well as the compute problem together. So I threw this one in. I don't know how many people of you know about the Tesla Dojo machine, the big AI supercomputer, but they've completely reinvented everything to do what they've done with this Dojo machine. And I'm just saying, if Tesla can do it, then why can't we do this in OCP? Now, I'm looking at 1 to 2 orders of magnitude simpler than what Tesla has done with Dojo, but we really need to try and innovate much more radically. So what I'm saying here is we need to innovate across the silos. And I'm a systems engineer, and my experience is that we're all in our little silos. We're very specialized in our silicon, hardware, power, thermal, software. And we live in our little one, and we're just stuck in our silo, and the walls of our silo, and we just think they're immovable. But what we need to do is we need to work across those silos, and so we need to break them down, and that's what we're trying to do in the HPC here. So hopefully this will become, a way to show you this in an example, and this is the example I use quite often, is we've got disaggregated racks. Disaggregation is very popular, but then you've got hyper-converged chiplets that are going on. So our traditional server is being pulled in 2 different directions, if you look at it like this. Disaggregation at the rack scale, basically that's what software engineers want, the ever tighter, reducing the power as much as possible is what the hardware people want. So yeah, so the rack is software composable. That's the nice thing about it. No resource goes stranded. On the right, but it's really expensive physical composability. You have to put chiplets in a package for millions of dollars. So composability is possible, but really, really expensive at the chiplet level. From a power baseline perspective, you're in the 5 to 10 picojoule per bits in a standard server. In a rack, you've got to move the data up and down the rack, so you're well over your 20 picojoules per bit plus. And the whole objective of this chiplet business is getting to the sub-picojoule per bit, so which is fantastic. And then if we look at latency, the baseline, if you take the server as a baseline latency, you've got much poorer latency on the disaggregation because you're going up and down the rack between the different memory and compute, et cetera. But you've got optimal latency in the chiplet approach. And finally, from a node volume, we've got the node volume of a 1U server going to a rack size, and you're going down to less than a cubic inch for these chiplets. So the way to look at this is the silicon technology has been shrinking and shrinking and shrinking forever, but we seem to have stood still for, the 19-inch rack is 100 years old next year. AT&T invented it. And we're still so tight to this makeup. So it's quite interesting. But really, the server is being pulled apart in two different directions. And you could be forgiven for thinking that the software guys who love this composability never talk to the chiplet guys. And you're absolutely right. We really do have two different silos going on here. And this is probably just one example. So what we're trying to do is, can we really break these silos down between these two worlds? And would it be possible to get the best of both worlds? Could I get the best of disaggregation and hyperconvergence from chiplet and the rack and pack it into a really small module? Could we not do shrinking of the system stuff? It's like we do shrinking of silicon, is really where we're trying to go here. So that's there's a quick picture of the OCP HPC module. So hopefully this presentation has just given you an idea of why. All right, this is what we need to do, and HPC has been very open as an industry, except for at the machine level. At the machine level, it's a very expensive proprietary machines from different vendors every year, and we're saying, can we get this into much more of an open modular standard with OCP HPC? So that's the motivation. Now I'm going to give you a little bit more detail of what we've done so far at the concept level. So let me get into that, give you an overview. So the high-performance compute module, it's modular, flexible, and composable. This is the key things of it. And it's protocol agnostic. It doesn't care what the protocols are. It's just trying to build a physical hardware device. And depending what processor or accelerator you solder onto the module format will give you your specific need for PCIe or CXL or OMI, etc. So that's one of the core ones. You can see that on the left is the module itself. So on the top is an example of a processor, a big power-hungry processor. It's in an OAM format. If you're already familiar with the OAM, we were inspired by the OAM format for this. But on the other side is there's lots of EDSFF connectors. So looking at the connectors a little bit closer, it's basically you can plug modules in or plug cables in. There is no motherboard. We've got rid of the motherboard. So the mezzanine card is there by itself. And this supports 320 transceivers today. And the only downside is the processors, from a memory perspective that's actually on board, it either needs to be HBM, actually on the package of the processor, or it needs to be serial attached memory, because this is a serial attached only to make it composable, so it doesn't support parallel DRAM. So that's the only drawback for this one. And then we put this together, and you plug these modules in or cables in, as you can see on the right here. And this is just an example of some E3 modules, some NIC 3.0 modules, and some cables wired together, which I'll show a little bit more detail on. Now, the reality is, though, hang on a minute, yes, this module could support, there's a big list of processors that it can support today that don't have parallel DRAM, basically. And don't forget, it could also carry up switches, PCI or Ethernet switches as well, if that was needed. So taking a closer look at the memory has tried to go serial many times over the last decade as HMC or fully buffered DIMMs. Well, it looks like it's finally made it this time. So that means the serial issue of serial attached memory is not a big problem. This is just showing you there's a parallel DIMM on the left. OMI that you've just seen has it it's been in production since 2019 in the JEDEC differential DIMM format. And we've proposed to put it also into the OMI format, 2 channels into an E3 module. That's your near memory, as was discussed earlier today. And then we've seen Gen Z, Smart Modular introduced Gen Z in 2020 in an E3 format, and Samsung recently announced CXL in an E3 format, CXL.mem in an E3 format. So, and that's for the fire memory. So we can see that our memory is going serial. So I think we're in good shape to be getting rid of the parallel memory here. This is just showing you the pieces. If you're not too familiar with EDSFF, it was an effort from Gen Z and a great guy called John Norton that really tried to get the industry to coalesce around this one connector and did a great job. So if you look at the OCP NIC 3.0, that uses that format, that interconnect format. And so does the storage, the SSDs from Kioxia and Samsung, et cetera. And you've just seen the memories, and you can also have I/O cables going into this connector. So that's great. And so anything in the sub-100 watt range is good in this module format. But where you've got your big processors, 200 watts to a kilowatt or maybe more, then they would go in the OAM format. They would go in the main module. Just taking a little bit more of an X-ray zoom in at the module, and I'll touch on this a little bit more, but the processor is actually very close to the connectors. So we have a chance here the Manhattan routing distances are less than 5 inches. So maybe we can actually get the connections down to 5 to 10 dB channels or 1 to 2 picojoules per bit, enabling a really low power. That's a potential future possibility if this module standard was adopted. Once you've got this module, again, if you're familiar with OAM, there is the OAI chassis out there. So our intent is, because we've complied to OAM in physical form size, we're hoping that we'll be able to slide one of our 8 of our modules into an OAI chassis. And so I'm going to show you a little bit more on that, of how we're achieving that. So what we're doing is we don't have a motherboard anymore, and so we need to re-architect, and we're going to start with the cold plate. So on the left is an OAM module on the top, and you can see a water-cooled version of the OAM module at the bottom, with all the pipes going between the modules to cool them. What we're proposing is can we put a heat spreader on the module itself to normalize to an interface that could be bolted to a cold plate, and just as shown there, and then we could build a water-cooled cold plate, aluminum cold plate, which also has the bus power in it, the 48-volt power delivery in it, and the water-cooled pipes. And we put the two together so you could get 8 modules. So the cold plate serves as a mechanical infrastructure to bolt the 8 modules to, rather, because there is no motherboard. And you can see the water cooling coming in there as well. Then if we flip the cold plate onto its backside, I've just done this, you can actually see that the bus bars there running through it are carrying the 54 volts. So this brings a really low resistance path. You don't need many layers in your motherboard. So it's a really efficient path to bring that high power into the system. You put by the way, I should say, on the beginnings of these slides, I put some names of the people that have helped us out. Molex helped us out tremendously with these diagrams, especially this one. People were concerned about the wiring. It would be a rat's nest. So this is actually the wiring of a fully connected topology, all-to-all, between the modules. And it may look, and it also has cables out to the QDDs and the OAI chassis, and also to the HIB cables to the HIB backplane as well, if you're familiar with the OAI chassis. No retimers needed at all, which is great news because of the cables. But it may look a little bit of a mess there, but when you plug the modules in, the EDSFF modules, the E3s, the NIC 3. There's some NIC 3.0s in the back, and there are some additional cables, and you've got the topology cabling. You can see that actually is very neat in the cabling. You can service this. This looks like just a bunch of flash, But at the bottom of each of those modules is a very high-performance processor. So it's just like that abstract diagram. It's almost as close as you can get to the abstract diagram that I showed you at the beginning. So hopefully that's given you a little bit of an understanding. And you can see we're shaking a lot of things up in the architecture here. We need the thermal guys to work with the mechanical guys and the electrical, as well as the silicon, as well as the software people. There's a lot of sideband management. So we are breaking a lot of eggs. There's a long way to go. But you got to start somewhere. And we're trying to build a community around that. So now I'll just cover a little bit more on the flexible interconnect, so you can get a bit better understanding of that. And then I'll hand over to Chris, who will touch a bit more on the thermal side. Chris is from Boyd. So on this presentation, I had a lot of support from IBM with some simulations of the channels, and also from Molex, again, with the 3D models. So thanks to everybody who's contributed to our open project. So let's take a look at this OAM, the OAM version 1 that we've got today. The OAM, there's OAM version 1.5 trying to get to 112 gigs. So there's growing demand for faster and wider interconnect. And the I/O is increasing percentage total of the actual total power. And that's a big problem. And so more I/O means more complex PCBs. The number of layers in these PCBs is pretty damned unbelievable right now. And the PCB losses are increased. They're a lot worse in cables. Cables are like 5 times better in terms of losses. And we're seeing this. So to go from these OAM modules to a QDD, we've got retimers. If you look closely, there's retimers on the board between the QDDs and the modules. And there's also retimers between the modules and the backplane that connects to PCI switches that are just on the other side of the backplane. So we're beginning to use retimers like confetti. And retimers, they burn power, they cost money, they add latency, they take up real estate, and they give us 0 value. So retimers are, if we're sprinkling retimers more and more, we've got the world is broken. That's my view. So we need to address that. So that's one of the motivations there. So zooming in on the HPCM interconnect. So I've already touched on this, but really the HPCM increases the system level density considerably. It's a 3D construction, so we're 3D at the system level. Not, we've got all this 3D going on at silicon. Let's do some 3D at the system level, guys. And we leverage this TA1002 interconnect standard, which is being adopted everywhere, which is fantastic. And we can leverage near stack. We've got the near stack PCI from motherboardless cabled fabric for the topology interconnect. And they're the ones on the corners. On the 2 edges, they're the near stack connectors. They're slightly more dense than the TA1002s for the topology routing. Looking back at this one that I touched on earlier, we're less than 5 inches. So we have a 10 dB channel opportunity here to reduce our I/O power, and possible further improvement. If this module, this could be a substrate. They can build substrates of this size now. So why don't, really this is just the OAM module is really just a new package which includes the power supplies and has high-speed connectors rather than solder balls. So why not get rid of the package and actually put your die down on the OAM substrate? That will give us even more budget back, so that reduce our losses further. So we did IBM kindly did some simulations for this for us, and some pessimistic ones with the package. And we're in the region of about 10 dBs at the 32 gig. So if you break it down into the individual pieces of losses, then you see the various contributions from each of the pieces. And then if you remove the package pieces, you can see that we could probably get in the 7 to 8 dB region going. By the way, that's going from the processor itself through the PCB of the module, through the TA1002 connector, across the PCB of the E3 module and into the ASIC of the E3. So the entire channel is down at 7 to 8 dBs. And so with this, a fully connected topology node like we've got here, so if we take each of the connections one at a time, so the cables between modules, the longest cable that there is in this system is of the order of 12 inches long. And you can go, I won't go through all the individual losses, but it's summarized there. But in green is a summary. The total channel loss on the worst case cable from processor to a neighboring processor would be 22.8 dB, which would give you a 7.2 dB spare on a 30 dB channel at 112 gig, right? So that's absolutely fantastic news because they've been struggling, got new PCB materials to try and get within the 30 dB budget. If we look at an OAI node with an HPCM module connected to the backplane, the host interface board backplane connection, and you go for the analysis there, again, these numbers are 112 gig based, although it's a 64 gig PAM4 for the PCI Gen 6 speeds. We can see that actually we can get to the backplane in 15.6 dBs, leaving 14 dBs to get across the HIB and into the switch on the HIB board itself. So we can be retimerless. There's no need for any retimers on this one. So we've got rid of those. So we've saved latency, saved power, saved cost, saved space. And then if we look at the routing to the QDD and we do the analysis there, we've got it takes 18 dB to get to the QDD. And so we've got plenty left, so we don't have to use retimers there either. And you've also got 12 dB spare. That may even support a passive copper cable linking two servers next to each other. So you could go retimerless all the way into a neighboring server between the two processors. Now, cable solutions, I've been told, that's unreliable. It's too risky, all those cables. Well, if those of you that paid attention to Power 10's, IBM's announcement of Power 10, you will see a horde of cables coming out of the packages themselves and going out of the chassis. If there's one company that cares about reliability, it's IBM. So if they can do it, then I'm sure we can also do it at this level of cabling. And now I'd like to hand over to Chris, who will talk a little bit about the thermal side.
Thank you, Alan. I'm Chris Chapman. I'm the product director for liquid cooling at Boyd Corporation. And we're really happy to be able to work with the HPC group looking at disruptive technology. Again, when we look at major architecture shifts, we actually have problems that are complex. And as we've learned through the keynotes yesterday, thermal packaging is at the forefront of what we're trying to do here. And when we look at some of the ideas and reshaping of the topography that we're looking at cooling, Boyd was able to take a look and say, there are some things that we can look at. And so we took on some initial...
Oh, you went the wrong way.
Sorry. We took on some initial feasibility. And so when we looked at the concepts that Alan and the team have come up with, the first thing we saw was the thermal spreader. And we obviously realized this is adding to an interface, especially when we compare some other cooling solutions for OEM modules. So that was certainly a first area. A thermal spreader is going to aid in the module approach and can add some benefits. And that could be a vapor chamber. Those are technologies that Boyd offers. So what we wanted to do is just take that off of our initial feasibility approach. But we do see that, again, there is a lot of benefit to having a module that supports and protects the module, makes it for easy upgrade. But for our thermal study, what we wanted to do is say, how can this compare to current cooling capabilities assuming that at the OEM level, performance is king. Now, obviously, there's a lot of other areas outside of compute, but we kind of took that compute view to really assess where we are thermally. And what we came up with was really a cold plate feasibility study based on existing process technologies that Boyd offers, and that is integrating what we would call a mesochannel cooling core into a cold plate and making this in an array. You can see the loop that we worked with the OAI group, OAM group, and Chen will be presenting later this afternoon some of the work that we've done. But you can see a direct liquid cooling traditional approach with a high performance cold plate. We want to look at moving that form factor into a flat plate and see where we are. And so that's the approach we're looking at. We're really super excited seeing bus bars requiring electrical isolation layers. I mean, this is definitely a great integration of functionality into a cold plate, and we certainly support that innovation. The first thing we needed to do was look at that core, right? There's a lot happening with the main processor, with the memory, and the other heat generating components are just as important. But our focus is if we have the mesochannel core, the copper core for the highest performance right at that main chip, and because we have liquid and a liquid interface within the rest of the aluminum cold plate, we can use the gap pad solutions for bridging thermally onto the module. So in this case, not having that thermal plate and reducing that interface says that we can create a similar interface because each module is self-loading. So we don't have the issue of having a coplanarity between each mesochannel core. The key is making sure that we have very good tolerancing at the mechanical interface, and that's individual to all 8 modules. So in our CFD analysis, we had to look at a different form factor because it's compressed in height, and the inlet and outlets are much tighter. As again, the whole liquid flow is within the array of the cold plate with localized cores. So it's not trivial just saying we can drop in this. We had to redesign it from scratch. This was a lot of work that we did to help validate it. The good news is we were able to get similar performance at that cold plate level, cooling that core as we would with a traditional direct liquid cooling. So that was very beneficial. The next approach is to say, what is the flow routing? So we looked at a 4x2 and an 8x1 matrix, which is similar work we've done with the OAI group. And what this allows us to do is to say, how are we going to route the fluid through these array of chips? And you can see that the blue graph is the 8x1. These are all in parallel. There's a tremendous pressure drop, almost twice as much pressure drop benefit in this flattened plate architecture than a traditional direct liquid cooling loop. And it's because the inlet and outlet were really, we have flattened tubes coming in and out. So the pressure drop in having a series of 4x2 is much greater, and that's actually a bigger benefit than what we see in direct liquid cooling. For a traditional loop, the 8x1 and 4x2 from the other group was around a 2 psi pressure drop. So we're seeing a greater pressure drop by, a pressure drop gain if we can run these in parallel, which is, again, another issue. We'll talk a little bit more. So once we're able to look at our CFD analysis, our flow network, we were able to look at the PQ curve. That's traditional pressure drop, looking at how we're going to route all of the liquid coming in and out through the cold plate. The next thing is we did a full characterization around the RQ curves. And what you can see is we've numbered the 8 modules. So you can see 1 through 4. In the 4x2, we're going to flood those first 4 chips with fresh coolant, and then the second 5 through 8 we'll see a temperature rise because that coolant will flow through 2 chips. You can see there are 2 different curves. In tan, they are for the lower thermal curve is for the first 4 and the second 4. And again, you would multiply that by half the power that you're seeing. The 8x1 you can see is lower, but you're the way the vertical axis, it is based on the total power, so you'd multiply that thermal curve by 8 times the number of chips. What happens is when you do that, if you just look at a delta T, that blue curve would be in the middle of those other two. And what that shows is an 8x1 is going to have all chips within a degree C of each other. That helps from a reliability standpoint when we look at a new architecture. So in summary, what we found was this is capable. This is capable to get the same performance as direct liquid cooling with the traditional loop approach that we see with the OAM modules. It gives us additional options when we integrate. We're integrating not only the bus bars, but now we can integrate leak sensors on the back. We can have a cap that protects it and collects any potential leakage. So whereas those are still issues if there is a potential leak, because everything is below the chips, any liquid, and we can immediately sense if there's any issue. The other thing that we can do is really look at the electromechanical requirements, because again, this is now a stiffener to the overall system and the electronics. So looking at robustness and reliability, how we attach it, those are all key areas of future investigation. A couple things we talked about, having all of this three-dimensional architecture. There is heat being generated by the top side of all of these other components. So one of the options that we could do is if we find that we're having an air temperature issue, is we can actually, because we have a liquid reservoir below, we could plumb a heat exchanger to actually cool the fluid, the air that's blowing over those modules. We can use heat pipes and I would say junction boxes into the liquid where we could move any heat from the top side. So as we see further hardware and we can empirically see where the hot spots are, we have plenty of capacity, in our opinion, to be able to bridge up and remove that heat adequately. And that's...
Just go last slide. Thank you.
Oh, okay.
Yeah, so just a call to action. Thank you, Chris. Much appreciated. Just a call to action. Really, please, we're a small community of small companies. We've got some, we really want to turn this concept into a reality. There's clearly lots of hurdles ahead of us, but we're breaking lots of eggs, like we said. So any help we can get from all the disciplines would be greatly appreciated. And we're also seeking some funding in order to build some proof of concepts and turn these concepts into physical realities and dig a little deeper into the issues and solve them. Okay, any questions? Thank you very much.